Okay, so welcome to the first session of Thursday. And we're happy to welcome Xingyu. Is that how you pronounce your name?
Yeah.
And talking about explicit near fully ex-Ramanujan graphs.
All right. Hi. Yeah. So I'm going to be telling you about some graphs. So yeah, this paper is kind of about infinite graphs, and like here are some pretty pictures of infinite graphs that will be covered in our setting. So yeah, in general, like we'll be considering infinite graphs with some sort of repeating pattern, such as the ones shown here. Okay, so the main theme of this work is that for all of these infinite graphs, I want to be able to construct finite graphs which resemble the infinite graphs in two different ways. So firstly, the graphical structure of the finite graphs should look like the infinite graphs in terms of the local neighborhoods. And I also want the spectrum of the finite graph to look like the spectrum of the infinite graph. Right, so let me just give you a very broad overview of what this goal is all about. So this question of whether we can find finite graphs which resemble the spectrum and structure of infinite graphs, it's a pretty natural question to ask. And we do know a classical situation where this goal has already been achieved. So it's been achieved by finite Ramanujan graphs, where a Ramanujan graph is just the best possible spectral expanders. And one way to characterize this is by comparing its structure and spectrum to the infinite deregular tree. So Ramanujan graphs look like the infinite deregular tree in the sense that the deregular graphs look like local pieces of the infinite deregular tree. And then they also resemble the spectrum of the infinite deregular tree because their non-trivial eigenvalues are bounded by the spectral radius of the infinite deregular tree. So in some sense, this statement is saying that the expansion properties of Ramanujan graphs are determined by the spectrum of the infinite deregular tree. And of course, so expander graphs are very important in CS theory. It has many applications, for example, in pseudorandomness and error correcting codes that I won't go into in this talk. And of course, there are also many known works about explicit constructions of Ramanujan graphs. For example, the classical works of Margulis and Lubotsky, Philip Stonerk, and Morgenstern, which constructed Ramanujan graphs for d-1 being a prime power. And also the work of Marcus Spillman Srivastava, and that was like de-randomized by Cohen, which gave constructions for bipartite Ramanujan graphs. And so yeah, for this paper, though, I'll be going at this with a slightly different angle. It turns out that random deregular graphs actually work very well for this kind of goal of trying to find finite graphs that resemble infinite graphs. So a random deregular graph is just a graph that can be constructed by summing up the uniformly random matchings. And it turns out that by a conjecture of Elon and a theorem of Friedman, that random deregular graphs actually structurally and spectrally resembles an infinite deregular graph in the sense that a random deregular graph is almost Ramanujan. That is like with epsilon, with like an epsilon additive error, it's almost as good as it can get in terms of the spectrum. And yeah, this happens with high probability. So a main part of this paper is finding a de-randomized form of this kind of work. So for Friedman's result, an alternate proof was given by Bordenave in 2015, and an explicit form of this proof was given by Mohanty, O'Donnell, and Paredes in Stock this year. So right, so that was the situation for deregular trees. And now the natural question you might want to ask is, so how do we find finite graphs that resemble non-tree infinite graphs? And we might want to find finite graphs that resemble more complicated infinite graphs, such as like this example right over here. It has this graph that has a for-click, and so it's like at every vertex, this graph has a for-click attached to it and a triangle attached to it. So we might want to find a finite graph that also has this structure, and we wanted to have like the best possible expansion. So eventually we'll be able to approximate many kinds of infinite graphs that are kind of like this, a very broad class of infinite graphs, including all like free products of finite graphs. So broadly, any sort of tree-like graph with a repeating pattern, we should be able to do this. And of course, you kind of need the graph to have a repeating pattern for approximation to even like make sense. So right. So one way to interpret this question is that I want an expander that has some sort of local constraints. Like I want the local neighborhood of my expander to look a certain way, but I also want it to have really good like spectral expansion. And these kinds of graphs do come up in theoretical computer science. For example, you can think of these graphs as some sort of typical instance of a random constraint satisfaction problem. Like you can think of this clique and triangle as a clause in a set problem, and then finding the eigenvalues of this graph will tell you something about the satisfiability properties of this random instance. Okay, so let me say a few words about what it means to spectrally resemble an infinite graph. So if I have this graph again, then the support of the eigenvalue I just drew this on a number line. It looks like this. The exact numbers are not important, but it's just there are two points, and then there are two intervals. So this is the spectrum of this graph G here. And then, so I'm drawing this as like a one-dimensional set. You might sometimes see this drawn as like a histogram, but I'm just concerned with the support in this work. So the goal is basically I want to construct a finite graph that locally looks like G, and it also, the non-trivial spectrum of the finite graph should look almost exactly like the spectrum of the infinite graph. So in some sense, I want to like match the gaps of the in the spectrum of the infinite graph. So as far as I know, I think this is not like really useful in like a TCS way, but it's like very mathematically interesting, I guess, to exactly be able to match the gaps of the infinite graph as well. And many previous works are only able to give you like matching the spectral radius and not the middle parts. Okay, so in a recent paper by Bordenave and Collins, they gave like a randomized way to construct finite graphs that satisfy this. And part of our work here is to de-randomize this proof. So I'm just going to very, very briefly tell you like one key idea that allows us to generalize from deregular graphs to these more complicated graphs. So the first thing you need to do is to like come up with some way to represent the infinite graphs. So it turns out that the way to do this is by using some sort of algebraic recipe, in particular using these matrix-weighted polynomials of permutations. So the idea for using these like polynomials, it's in the paper by Bordenave and Collins, although they present it quite differently, and they also don't talk about what kinds of graphs you can obtain from this representation. So we'll eventually see that by doing this, you can obtain a very large class of graphs. And part of our contribution is to investigate which graphs can and cannot be constructed using these kinds of recipes. Okay, so the idea of these polynomials of permutations is that I want to write the adjacency matrix of the infinite graphs as a polynomial of infinite cyclic permutation matrices. So properly speaking, these are going to be the matrix representations of the free group generators. And so you can just think of it as I have a polynomial and I plug in some infinite permutation matrices, and this gives me a adjacency matrix of an infinite graph. And then because like I had these infinite permutations, like the natural way to try and create a finite graph is to like sort of subsample the infinite permutation by replacing the infinite permutation with a finite permutation. And the random construction in Bordenave-Collins' paper is to just use a random finite permutation in place of the infinite permutation. And they further like generalize this by, so not only do I have a polynomial, the polynomial is supposed to be matrix weighted. So for example, I have this polynomial here. It has like, it's like a bunch of variables. It has a bunch of weights, and each of these weights A1 to AD are matrices. So we will evaluate this as you take each of these A's is a matrix, and then you plug in the permutation matrix here, and then you take the tensor product. So this like evaluation is kind of independent of the dimension of the permutation and also in the dimension of the coefficients. And after you do this, you interpret the resulting matrix as the adjacency matrix of a graph. And it turns out that if you do that, you can use it to construct all kinds of infinite graphs, like all of these pretty pictures that I showed you earlier in the talk. And then, so what happens in Bordenave and Collins theorem is that they showed that for any matrix polynomial, you can construct, if you sub in the random permutations, you get this approximation in Hausdorff distance, which is like this closeness in the sets of the eigenvalues that I talked about earlier. And it just says that every eigenvalue of a random like permutation plugged into one of these matrix polynomials, it's almost exactly where it's supposed to be in terms of the infinite graph. And so our results is that we show that, firstly, we show that what infinite graphs can matrix polynomials generate. And it turns out that it includes a super wide class of graphs that are considered in the literature. And we also show some necessary conditions for graphs to be able to be constructed in this way. And then secondly, the thing we do is that so Bordenave Collins had this thing where they use random finite permutations, and then we construct the random permutations in like explicitly, so that we know exactly, we can deterministically construct the permutations that you need to plug into the polynomials that will give you the good like finite graphs. All right, yeah, so this is thanks for do you guys have any questions?
Yeah, so we have a few time for questions.
I have a question.
Yeah.
Can you say a bit about what Hausdorff distance means? And is it something? It sounds like it's something stronger than just matching the support, or?
Yeah. Oh, Hausdorff distance is this matching the support
okay.
that I'm talking about. So it just means that I want to match all of the gaps, and I want, like, for example, there's like an interval here, and I want to have all of my eigenvalues like fill out the entire interval. So it goes like both ways. Yeah.
I see. So it doesn't capture anything about sort of the density of eigenvalues beyond the support.
So it's somehow using, by the proof technique that we use, eventually you can show that the spectral measures are actually converging to the infinite graph. But this is like, yeah, this is part of the proof and not exactly the statement. Yeah.
I see. Thanks.
We have some time to take a few more questions if you have.
Sure, yeah. If I could ask a question. Oh,
No, go ahead, Nick.
Okay, thanks. Sinyu, so do you have any sense of like sort of what the next class of graphs that you would like to study with these techniques? So you can handle this sort of class of graphs that comes from these polynomials. Is there sort of a next step of infinite graphs that you would like to investigate next?
I guess like one thing is like trying to think about how to like generate, say, for example, like simplicial complexes with this sort of like randomized polynomial sort of technique. I think that could be very cool.
That does sound, yeah, that does sound cool. Cool, thanks.
Yes, my question is maybe an extension of Nick, but it's more maybe about Bordenave Collins. Like, how crucial is the complete randomness there? Is there any hope for buildings, or to take get finite analogs of these high-dimensional expanding buildings? Because we can't expect random ones, but yeah.
What do you mean by how crucial is the randomness there? Because I guess like we de-randomize their like randomized constructions and.
I understand, but in some sense, like they're using the fact that a random graph is a very good expander. But a random graph is not, or a random high-dimensional expander or hypergraph is not a very good analog of a building.
Right. So I guess it's like the idea is maybe just like there could be like a class of random graphs. Okay, if we can find like some sort of like distribution that is like good, I guess. So I mean, I guess that's already a very like sort of big open problem in this area. But I don't. So I mean, I guess the idea that from this Bordenave Collins paper is that like they're like, in order to construct these sort of structured random graphs, they have to first go to this like algebraic representation, and then they plug in like random permutations. So it's like sort of a hybrid approach of like an algebraic, but then algebraic structure, but then like also a random distribution. So yeah, I guess I sort of vaguely am thinking about whether you can use this sort of idea to get a random distribution over buildings.
Yeah, that would be great.
Okay, let's thank the speaker. And move on to our second talk for today.
You hear me?
Yes, so
Okay.
Dean will talk to us about nearly optimal pseudo-randomness. Sorry, my timer went off. From hardness.
Thanks, Alexandra. This is joint work with Dana Moshkovitz, Justin O, and David Zuckerman, all from UT Austin. Okay, so as you probably know, sorry, just let me, my Zoom got stuck. Okay, yeah. So as you probably know, randomness is a valuable resource, and it's often essential in important applications such as crypto, property testing, and other stuff. But regardless, it's incredibly useful. Sometimes efficient algorithms or randomized algorithms are all we have, and the deterministic counterparts take exponential time. But also it's often faster and simpler in practice. For example, take primality testing. We have a nearly quadratic, rather simple randomized algorithm, and the deterministic one is sophisticated and takes considerably more time. So even if or when, hopefully, we prove BPP equals P, de-randomization may incur an inherent overhead in running time. And in fact, it does incur an inherent overhead in running time under complexity theoretic assumptions. And our goal is to get that optimal, to get the optimal overhead explicitly. So just so we're on the same page, our model of computation is two-sided error randomized algorithm. And we denote by T, the runtime of our algorithm. And we also assume it tosses T random coins, just for simplicity. And T corresponding to polynomial in input length is just the class BPP. And our result also extends to larger T's. So under complexity theoretic assumptions, BPP equals P. And this follows from the celebrated hardness to de-randomization paradigm. Meaning that every polytime algorithm can be de-randomized with a polynomial overhead, polynomial slowdown. So a bit more formally, suppose we have some function in d time 2 to the O of n that requires exponential size circuits. Then we can take any randomized algorithm that runs in time t on inputs of length n and simulate it deterministically in time polynomial in t and n. And this polynomial is rather large, it's at least 8. And this is what we call a large polynomial overhead or a polynomial slowdown in the de-randomization. And other proofs of that sort of result also yield large overhead for reasons inherent to all existing techniques, and I'll briefly talk about it soon. And the question is, can we de-randomize with small overhead? And in fact, we can. So what's our result? Assume we have some function in d time 2 to the 1 plus alpha n, and alpha here is a small constant, that doesn't have circuits of size 2 to the 1 minus alpha n. So we are at the high end assumption. Then we can take any randomized algorithm and de-randomize it with a slowdown of, so t is what we, the original running time, and a slowdown is the maximum of t and n to the power of 1 plus O of alpha. So we call it nearly linear slowdown. And there is an important caveat here that we assume this, the function is hard against circuits which are seemingly stronger. So we assume hardness against the non-uniform analog of NA cap Cohen. So let's talk about optimality for a second. A linear overhead is sometimes necessary under assumptions. Let's consider the problem of univariate identity testing, which is testing identity of two arithmetic circuits with one variable degree n, O n wires over a large field. It has a simple nearly linear randomized algorithm and a nearly quadratic deterministic one. So there is a gap here. And Williams showed that coming up with a deterministic algorithm running in time slightly less than n squared would refute an assumption called NSEF. Okay. We also give a result about so assumed on top of the fact that we have a hard function, that we're guaranteed that the algorithm errs on at most 2 to the t to the 1 minus O of alpha, and compare it to the usual 2 to the t over 3, which we have in BPP. We can de-randomize tiny slowdown, and not only that, we get to assume hardness against a weaker class of circuits. And here we only need to assume hardness against NP cap Cohen P. Okay. So hardness-based black box randomization follows from pseudorandom generators, PRG. So I guess most of you are familiar with PRGs, but just a recap. So a PRG is short seed, the seed of bits, uniform bits, to n bits, such that any distinguisher from some circuit class, function class C, cannot distinguish between the uniform distribution over n bits and the generated distribution. And in order to randomize algorithms running in T, what we need to fool is the class of circuits, it turns out, of size at most roughly T. And if we have such PRGs, the randomization is easy. Place the random coins with the image of the PRG. So instead of iterating over all 2 to the t random strings, we only over 2 to the d choices, and then take the majority. And if we do so, the running time is t, which is the original running time, times 2 to the d, for d being the seed length of the PRG. So the seed length of the PRG dictates the de-randomization overhead. And you can view such PRGs in transforming hardness into pseudorandom bits. And previous PRGs do this suboptimally. So if we assume maximal hardness, the seed length will still be C log T for a large constant C. And this is the large overhead, which is not good in practice. As I said, at least 8 or something. And we managed to transform nearly all hardness to pseudorandomness. So you see that assuming F is hard for such circuits, we see length almost log T, 1 plus alpha log T. The downside, again, we assume F is hard for a class of circuits. So let's talk one slide about the previous techniques. And previous PRGs utilize the connection to what's called locally decodable codes. And generating one pseudorandom bits we can do with a short seed, with the good seed, by encoding the truth table of F and choosing a bit of the encode. But we need to sample T bits from the encoding of F. And this has its barriers. And one main barrier for getting optimal parameters here in this paradigm is the argument. And it's inherent to the proof technique that uses locally decodable codes and then stretching it to T bits. And what we do is we obey the heartbeat argument by first shooting for a Wheeler object, what's called a pseudo-entropy generator, which was suggested earlier by Barak, Shaltiel, and Victorson. And we call it in a PLG, output is computationally indistinguishable from the uniform distribution. In a PG, it's a weaker guarantee, and the output is computationally distinguishable from, now we need to be careful, or any distribution with high entropy. I'm not going to get into the specific definition, you can see it in the talk or in the paper, but I'll just mention that PGs by themselves already suffice for de-randomizing algorithm that err rarely. In fact, it's an equivalence. So what's our PRG in a very high level? So we take our hard function f, construct a PEG, invest a short uniform string, and then purify the high entropy, the high computational entropy distribution with an extractor, which takes another uniform string, and then output the result. So you can see here, and I also wrote down the seed length of each primitive. Okay. So just key components that we have. So connection between PEGs and error correcting codes, specifically list recoverable codes over large alphabets, which we show give PEGs. We construct such codes, which I'm not going to define. I'll just mention that they have non-standard parameters for our application to be successful. And this is where we utilize non-uniformity and non-determinism. And once we have PEGs, we use the seed to sample uniform symbol of the encoding, like before. And we also need to show that using an extractor works. We prove that we can indeed apply an extractor. And one last thing, very recently, Chen and Tel added cryptographic assumptions to improve the de-randomization time even further, which is significant when T is very large, for example. And they also show a comparable lower bound. Again, of course, under some assumptions. So now that we have roughly the correct runtime overhead for randomized algorithms, one of the main open problems that remain is, can we get the same result, the same de-randomization overhead, but assuming hardness for deterministic circuits? This is one open problem I'll conclude with. Okay, thanks.
We have a few minutes to take some questions.
Sure, I'll ask a question. Is there anything you can say quickly about how you construct the locally list recoverable code? Is it somehow based on previous codes, or is it really sort of special and tailored to your situation?
No, it relates to previous codes. Actually, we start with local list decodable codes and fold it in some way. Yeah, we essentially fold locally list decodable codes over small alphabet to increase the alphabet size, and then we argue for list recoverability. Again, we need to handle very very large lists, so we kind of take advantage of both the non-uniformity and the non-determinism in our proof technique.
Cool, thank you.
I see there is a chat question, so do you want me to answer it or answer it
Yeah, you go
afterwards?
ahead and answer the chat question since we have it.
Okay, so a
And
PG
I think
string
Salil also has a raised hand.
So go ahead, Salil. I'll answer the chat question after.
So, Dean, is there any intuition or possible direction towards understanding, now that we need, know we have this evidence that you can de-randomize with just this quadratic or nearly linear slowdown, maybe which randomized algorithms actually need that kind of slowdown versus which ones maybe could be de-randomized at a just a polylog overhead?
Yeah, that's a good question. I don't have a good intuition. As I said, we have algorithms which we know under assumptions. This is crucial. Univariate identity testing, also normal identity testing. We also have graph algorithms which we know we can de-randomize to run in linear time, which is great. Yeah, it's a good question. I don't have a good intuition. Sorry.
No, yeah, open-ended
So
question. Thanks.
Have to move on to the next talk, but if you have more questions, perhaps like Slack channel or chat would work. So let's thank the speaker. And our next talk, we will learn, Lisa will talk about correlated pseudorandom functions from variable density learning parity with noise.
Hi, thank you. Can everyone hear me? Okay, great. So yes, I'm very happy to talk about correlated pseudorandom functions from variable density learning parity with noise today. This is joint work with my wonderful co-authors, Ilette Bolle, Geoffroy Couteau, Niv Geboa, Yuval Ishai, and Peter Scholl. And so this talk will also be about randomness, but this time correlated randomness. So for example, you can think about tuples AC0, BC1 that are uniformly random conditioned on C0 plus C1 equaling the product of A times B. And of course, producing such tuples just like this is trivial, but the problem is how can you generate correlated secret randomness? So in a way that Alice here, the party on the left holds tuples AC0 and Bob holds BC1 that are in this correlation, but such that Alice does not know BC1 and vice versa. And such correlated secret randomness is very useful, for example, in the context of secure computation, allowing two parties to securely evaluate a function on private inputs without revealing anything beyond the function output. And this gives something very efficient, but the problem is that it requires a lot of this correlated randomness, and it typically requires a lot of, in particular, communication and storage. And in order to overcome this issue, one can use pseudorandom correlation generators, which allow to extend short correlated seeds, S0 and S1, to long correlated pseudorandom strings. So what does it mean? So first of all, if you zoom in and one part of the output, then you will indeed have that Alice will have AC0 and Bob BC1, such that these are correlated in the wished way. And in order to be useful for secure computation, again, we want that even if given the one seed, the output of the other party still looks uniformly random from here, the view of Alice, and vice versa. And this is a very useful primitive and already gives a lot, but it's somewhat limited in two respects. So it only supports a one-shot expansion. So you either if you don't need all the randomness, you either have to store it or recompute it later, and this inherently limits you to limited, so to polynomial bounded stretch. So to overcome these issues, what we did in this work, introduce the notion of a pseudorandom correlation function, which now allows which basically gives the parties correlated pseudorandom functions. So the parties now hold correlated keys K0 and K1, such that if they evaluate on any input X, then they will get tuples AC0 BC1, again satisfying the correlation. And as before, the security will guarantee that BC1 is hidden even given K0 and vice versa. So it looks uniformly random, conditioned on being in the correlation. And so in particular, now this gives iterative expansion, and therefore allows virtually unlimited stretch. And now the question is, of course, defining a primitive is easy, but how do we get that? And what I want to note here, so other than going from pseudorandom generators to pseudo-random functions, there is no generic transformation. So it's not possible to reuse parts of the output again, or have GGM-like construction to get from pseudorandom correlation generators to pseudorandom correlation functions, because the correlation of the seeds will be a different correlation than the output correlation. So what we do in this work is first we show a generic construction of PCFs given a weak pseudorandom function together with a function secret sharing scheme, where weak pseudorandom function is a keyed function family, so that if you take a random function from this family, then this function will look on random samples. It will look like a random function. So it's like a pseudorandom function, but the adversary only gets access to random outputs. And the second and the second building block is function secret sharing scheme that basically I will not have time to go into it in detail, but that basically allows to generate compressed additive secret shares of a function. And to give a very rough intuition, the weak pseudorandom function will give the randomness, and the function secret sharing scheme will give the structure that allows to set up this correlated sequence. And the hard part is not actually coming up with this construction, but the hard part is instantiating it. And you can instantiate generically using any weak pseudorandom function of your choice, and using a heavy hammer function secret sharing scheme. So this can be constructed based on learning with errors, and is computationally quite expensive, but on the bright side, it supports all functions. So you can use it with any weak pseudorandom function. But as learning with errors is kind of the assumption that gives you everything. A question is, can we get it from other assumption, from potentially weaker assumption, and also can we get a better asymptotic or even concrete efficiency? And in order to do this, we kind of start the other way around. So we start with the low-end function secret sharing scheme, and which can be based on the minimal assumption of one-wave function, and is also concretely efficient, but it's very limited in the function it supports. So, for example, it can support point functions, which are functions. So here, PF alpha is a function that is one only on input alpha and zero everywhere else. And what we do is we propose a new weak pseudorandom function candidate from what we call the variable density learning parity with noise assumption. And so what is the variable density learning parity with noise assumption? It looks very much like the dual learning parity with noise assumption that states that if you have a matrix, a flat matrix, and multiply it with a sparse vector, then the output will be close to, will look computationally indistinguishable from random. But the dual LPN assumption inherently limits you to polynomial stretch. And so what we propose is a variable density candidate, where after each step, so you see here 1, 2, 3, 4, 5, 6 intervals, and every of this interval is double the length of the interval before. And here the blue and the red should be non-zero values. So you see on the left-hand side it's very dense, and if you go to the right-hand side, it gets sparser and sparser and sparser. And the idea or the intuition behind this construction is that it both allows to go beyond polynomial stretch, while still having it computable in polynomial time, because the matrix on the right-hand side will basically be exponentially sparse, but still get something that is not biased towards zero. So yeah, I wrote it like if you look at it now, it looks like more like a pseudorandom generator with an exponential stretch, but you can just view the inputs x as a row of the matrix, and the vector you can view as the key. And yeah, as I said, this allows up to a sub-exponential stretch. And why is this function secret sharing friendly. So if you look here, basically you can write this as a sum of the multiplications of lots of unit vectors, because every of this interval is represents just a unit vector. And as the product of two unit vectors is just one if xij equals to kij, this can be written actually as the sum of point functions. So the point functions that is defined by the key kij evaluated on xij, and this will also be exactly 1 if kij equals to xij and 0 otherwise. And I already promised. I don't know if you noticed on the title slide that you can also we also give a low complexity weak pseudorandom function, and to really see that you can again view it in another notation, namely the product of unit vectors. Again, you can also view as a bitwise comparison of the bits. So you can write it as the end, where e is the where 2 to the e is the dimension of the vectors. Then you have e bits over which you go, and these like basically corresponds to multiplying longer and longer vectors. And if you write it like this, you can see that if you consider the key as fixed, then this is a depth 2 WPRF candidate in AC0, and which is something that was not known before with sub-exponential security. And because I briefly mentioned that the motivation is also to think about concrete efficiency. So this can actually give something concretely efficient. If you compare it with pseudorandom correlation generators, we get slightly larger key size, so 120 kilobyte compared to 40 kilobyte if you're interested like to expand up to 2 to the 30 samples. But the evaluation time is now roughly 8,000 PRG operations per sample. So it means you can do around 20,000 of those PCF evaluations per second. Whereas with the PCGs, even if you only want to evaluate like a single point, you need to do a number of PRG evaluations that corresponds to the output length. So here 2 to the 30 PRG evaluations, and of course this gets worse if you want like if you want more stretch. And yeah, so to conclude the talk, in this work, we introduced a new variable density learning parity with noise assumption. We proved that it withstands a large class of attacks. Because it is function secret sharing friendly, it leads to concretely efficient pseudorandom correlation functions. It gives a new low complexity weak PRF in AC0 mod 2, which was not previously known with sub-exponential, which can be conjectured to have sub-exponential security, and something that I did not have to time to go into today, but it also implies PRGs and weak pseudorandom functions with security against XOR related key attacks. And for this, I refer to the paper or the longer version of the talk. And so with this, I'd like to conclude. Thank you very much, and I'd be happy about questions.
Thank you. Yeah, let's take some questions in the next few minutes.
I have just a tiny question about the pseudorandom correlation function, just in terms of the notion, the way you kind of, the way we kind of presented it, it seemed like for every X, you have the same correlation, the particular one that you're proposing. Does that also support, different correlations depending on X?
So we have, so generally, like the way we consider it now, you get the same correlation for every X, but we also give I think I have to think about it. So we also give a PCF where you can like universal degree two PCF. So you don't have to, you can like later decide which polynomial you want to evaluate on a function. So this gives you some flexibility in what you want to evaluate. But for kind of the most efficient instantiations we have for Wole and OT where you really get the same correlation for each other.
Correlation, but kind of computationally independent.
Yeah, actually,
yes.
The Wole example, there is actually a correlation, right? It's like the same.
Yeah.
The Wole, there is one of the things that Lisa mentioned does have correlation between instances.
Correlated.
So yeah, sorry.
Yeah, please.
So for Wole, it's like all E, but where one of the inputs is fixed. So across all, so for all E, the one I showed, in every you have a fresh A and B, and then C0 plus C1 that adds up to A times B. And for Wole, you can choose the same A across all instances.
Okay.
So yeah.
Thanks.
Thank you for the question.
Are there any more questions? I guess we're out of time also, so perhaps we can take the rest of the questions offline, and let's thank Lisa.
Sorry.
So our next speaker is Andrew, and he will talk to us about an improved exponential time approximation algorithm for fully alternating games against nature.
Thank you. Thank you, Alexandra. I'd like to first, am I audible? Okay. So I'd like to thank Rahul Santanam of Oxford for many helpful discussions around this work and for and support for this work. And I want to begin with the notion of fully alternating games for two players. And these are games in which players P1 and P0 take turns choosing binary moves for some fixed predetermined number of steps. So the outcome of the game is then given by a payoff function for player one. So it's a Boolean function f, which tells you for any possible sequence of moves, whether player one wins or not. This is known to the players, but there's also the associated computational problem where we are given the function, typically succinctly as a circuit, and we want to determine the value of the game for player one. So in the traditional adversarial version of this, the player zero is having to pay player one and wants to minimize this payoff. So under optimal play, it's natural to define the value as this alternating max-min expression in terms of f. In terms of its complexity status, computing this is p-space complete if f is given succinctly by a circuit. And moreover, it seems to need time exponential in the number of moves to evaluate. But we at least know that you can evaluate this more efficiently than pure brute force. So building on earlier pruning ideas in the community, Sneer showed and Sachs-Wigderson optimized that you can evaluate with an exponential savings over brute force. And this is part of the kind of bedrock of game tree search. This is also the best you can do for this problem. So for black box anyways. So we understand the situation quite well. But now today I want to talk about games against nature, which is a related setting that we understand less well. This is the case where player one, as before, is trying to maximize their payoff, choosing binary moves. But now player zero is moving completely at random, in fact, uniformly at random. So this is an indifferent nature, we can say, following Papadimitriou, who studied the complexity classification of these problems. Now, this can model ongoing interaction with some kind of physical or other system, provided we have some sort of reasonable statistical description of how the system behaves. So we can't predict nature's moves, but we have a probability distribution on future events. And we also assume some observability on nature so that we can see nature's moves. So now it's natural to define the value as this alternating max and averaging or expectation expression. And these values, which I should stress, now player 1 is playing with the knowledge that player 0 is nature and is trying to take and player 1 is trying to take full advantage of the assumption of random play. So these game values for the first player are also piece hard to compute, and even approximately. This follows from taking the IP interactive proofs perspective and the IP equals P space breakthrough of these authors. Let's see. So this has been studied in several allied overlapping areas, and the best understood paradigm for giving algorithms for this type of problem is that of Markov decision processes, where we assume that there's some underlying evolving state of a system with a not too large state space, where the system evolves according to or in response to the moves of both the player and the and nature. And so there's a series of incremental payoffs to the first player, and we want to maximize the sum or the average of these. So we basically, we understand how to solve these kinds of problems by dynamic programming. Okay, so, but in this work, I'm trying to push the envelope of unbounded state space. Games like chess, where the state space is kind of as large as the game tree itself. So when f is given by a Boolean formula, this problem is very expressive in general. It's known as stochastic SAT. And Littman, Madrusik, and Patasi gave an improved algorithm to estimate these game values, not for the fully alternating binary case, but in cases where there are not too many player 1 strategies as a result of the structure. Like if all the player 1 moves are towards the beginning, this reduces the number of player 1 strategies. And they give other algorithms with experimental evaluation, and they're not the only authors to do so. I'll mention that game against nature values can also be reduced to the longest common subsequence problem, as shown by Abud and Rubinstein, and to the longest increasing subsequence problem, both of which have interesting algorithms developed, but they're not sufficient to yield improvements for this fully alternating case that I'm discussing. So it remained open whether there was some kind of exponential savings, some improvement akin to that of Sneer and Sachs-Wigderson for these games. And that's what I provide here. So there's a randomized algorithm which takes as input one of these payoff functions, makes an exponential but improved exponential number of queries to f, okay, 2 to the 1 minus delta n, where n is the number of Boolean moves, and outputs a certified lower bound on the game value, which in expectation over the algorithm is within an exponentially small distance of the true value. All right, so this works on any bounded function. The boundedness is essential. It can also compute near optimal strategies and tell you how to move, not just what your value is going to be. So the guarantee here is by nature additive and not multiplicative. That's essential. I don't think it's a serious drawback because it's going to be a multiplicative guarantee as long as the value is decently large. More serious drawbacks, the delta in this improvement is currently tiny. I haven't optimized it, but I just don't know how far it can be pushed. In particular, you know, I still don't know whether this problem is easier or harder computationally than the original adversarial play notion, right? So can this constant be pushed to where it is for 2-player zero-sum games? I don't know. Also, the algorithm is exponential space. It's not space efficient, unlike that of Sneer, which is polynomial space. Okay, I guess, I hope that if questions appear, I can see them, but maybe I need to hear something from the audience. So I'll go on. In this work, it's convenient to pass from the function table perspective on this f, the payoff function, to this so-called MA formula perspective. So we now transform to a picture where we have this function which is defined by an alternating tree of max and average gates, as depicted here. The A gates are unweighted averages of their two inputs. The individual payoffs in the function table are replaced with real values x1 through x capital N. And now our goal is to approximate the MA value of an input x with few queries to x, with a polynomial query speedup. All right, x corresponds to the payoff function f. And here's the k equals 2 example for illustration. So the first basic idea in this work is that of certified lower bounds for this formula. So I've here given a partial view of an input, and from the assumption that the inputs are all non-negative, and the fact that this is a monotone real formula, we can get a lower bound just by replacing unseen bits with 0. So all lower bounds used in this work are of this type. A next basic idea is that of all queries algorithms. So even though our final goal is a query efficient algorithm, we're going to be iteratively building algorithms which make all of their queries and measure their progress over time. So we can graph the lower bound approximation error or defect between the certified lower bound and the truth as a function of time, as depicted here, for some particular execution. All right, so our goal is a point guarantee of this form, that the expected defect after some small number t of queries is at most some small epsilon. And we'd like that to hold across all inputs. And so we approach this goal by more modest algorithms, which have quantitatively more modest guarantees, but guarantees from multiple points in time. So this is a profile of an algorithm that has 3 guarantees associated with it at 3 separate points in time. Okay, and we also break time into epochs associated with these chosen endpoints. So we can talk about the first through the fourth epochs here. This is not just for analysis purposes, but it actually structures our recursive family of algorithms. So let me talk about composition of algorithms. So the main bootstrapping step to get better and better algorithms for larger and larger inputs is a tailored notion of composition, where we have an inner algorithm, which was working here on the subtrees for the MAK problem. And this inner algorithm is assumed to have defined epochs as described. The outer algorithm is going to be working on the top subtree. It's going to be taking the viewpoint of the top of the tree, and it's going to be an algorithm for MAL, but of a special type, which I'll discuss in a bit. We build a composed algorithm for the larger input size, which maintains parallel simulations of the inner algorithm on each of these small gray subtrees. So, and this parallel simulation idea is where the exponential space creeps in as we iterate this idea recursively. All right, so this L here is going to be bounded by a constant in our work, but huge, all right? And it's essential that this L be constant for the efficiency that we want. Whereas K is going to be larger, and moreover, it's going to grow with the recursion depth. All right, so in a basic step or subphase, we're going to use the outer algorithm to choose a next subtree and advance the simulation of the inner algorithm by a whole epoch. All right, so the epochs of the inner algorithm structure our composition. And in the phase R of the composed algorithm, all such subtrees complete their rth epochs in some well-chosen order. So we pick some subtree to advance epoch 1, another one, and this is the end of phase 1 of the composed algorithm. And phase 2 is similar. And the order is dictated by the outer algorithm. All right, and this composed algorithm is going to have epochs associated with it. It's actually ends up being best to end the second epoch of this composed algorithm midway through phase 2. In fact, towards the end of phase 2. And this will give p plus 1 epochs to the composed algorithm if the inner algorithm has p. So the outer algorithm is going to be using the old certified lower bounds on the subtrees as a kind of baseline advice to choose queries which advance us to the next certified lower bounds after the next epoch. And so we're going to let X and Y now denote these inputs which the outer algorithm is using. It's going to query all of Y in some order, and its main objective is to get a large MA value of the hybrid input, where we start with X and we start incrementing to the Ys, and we're going to measure the quality of the MA value after some n minus E queries, where n is the total number, and E is on the order of root n. The kinds of inputs that these algorithms get are described by a probabilistic notion of alpha-beta ensembles. So briefly, we have a pointwise inequality between x, y, and z, where x and y are vector random variables, and we have pointwise expected distances between each coordinate and some true values z. All right, well, you can see them below, and you can interpret the x's as approximations to the true value after epoch r, and yj after epoch r plus 1, focusing on the jth subtree. So this is the type of inputs that we get from our process. And a steepener algorithm, briefly, is an algorithm which looks at the bits of y in such order, in some well-chosen order, and gets a nice guarantee on the expected gap between the true MA value and the MA value on the hybrid viewpoint after n minus E queries, which is nudged just a little bit better than you'd expect towards the smaller of the two expected guarantees on the individual coordinates. So pictorially, we have these epoch defect bounds for MAK, and we get new ones for the larger input size, first by passing to a fraction of queries for normalization. And then you'd expect some kind of interpolation between the endpoints, because we're advancing from the rth epoch on the subtrees to the r plus 1. This is not hard to obtain, but what our steepener does is actually nudge us a little bit better, a little bit towards the smaller defect bound. It steepens the approach. And we get a new analysis profile for the composed algorithm. And let me just briefly say, since I'm out of time, I think, that that we essentially give such a steepener when the L is sufficiently large. But to do this, we need to actually revise the picture and replace the bounds on expected gaps between certified lower bounds and true values on the subtrees. We need to replace these with moment bounds, saying that we have some nice concentration behavior. Okay, and we require an exponent in the moment to be sufficiently large compared to the gap between our two guarantees. But if we do this, if we make such a stronger assumption, we're able to replicate it in the conclusion and actually boost the concentration parameter by a root n factor. So the estimates produced by this algorithm get progressively more concentrated, which is a useful and usable insight into how the algorithm actually makes progress. So I think I'll have to pause and take questions or cede the floor.
Thank you, Andrew. Unfortunately, we don't have time for questions. So if people have questions, would you mind if we take them offline or through chat, Slack, whichever of these channels, so that is that okay?
Mm-hmm.
Okay, so let's thank the speaker. And we have our next talk where
Hi.
I'm not entirely sure how to pronounce your name.
My name is Shai.
Shai, okay.
Yeah.
Will give us a talk on a dichotomy for real Boolean Holland problems.
Yeah, thanks. Thank you all for attending my presentation. Can you hear me? Okay.
Yes.
So I'm going to present a complexity dichotomy for real Boolean Holland problems. It's a joint work with my advisor, Professor Jingyi Cai. So Holland problem is a framework for counting problems. Such a problem is parameterized by a set of Boolean constraint functions, also called signatures, denoted by script f. Each signature of right n is a map from the n-dimensional Boolean space to the complex field. An input of the Holland problem specified by a signature set script f is a graph where each vertex is labeled by some signature from this signature site. And for this graph, we consider all 0, 1 edge assignments. Each assignment gives an evaluation, which is the product of labeled signatures over all vertices. So this is the product. And the output of this problem is the sum of products over all edge assignments. So totally there are 2 to the number of edges, many assignments. So this is a sum product computation. Now let's see an example. Approximation of a graph is just a set of edges such that for each vertex, exactly 1 edge incident to it is selected. And in this graph, the set of red edges is the perfect matching. Now, if we want to count the number of perfect matchings of a graph, then this problem can be expressed as the Holland problem parameterized by exact 1 functions. So for exact 1 function, this function takes value 1 when the input has Hamming weight 1, and it takes value 0 otherwise. So the Holland problem, this Holland problem is just the problem of counting perfect matchings. Why we are interested in Holland problems? Well, it's a very expressive framework for counting problems. While problems expressible as Holland problems include counting graph homomorphisms, counting constraint satisfaction problems. These are the 2 well-studied frameworks for counting problems. And also counting matchings and counting perfect matchings, and counting weighted Eulerian orientations. And also there are lots of models from statistical physics, like 6-word models and 8-word models. The computation of their partition functions are also counting problems, are also Holland problems. And more importantly, it's proved that counting matchings cannot be expressed by counting graph homomorphisms. So Holland problems are probably more expressive than counting graph homomorphisms. And for an arbitrary signature set script f in a large class, we want to classify the complexity of the Holland problem specified by the signature set script f. So such a classification is usually stated as a dichotomy theorem, which means that for a large class of signature set f, the Holland problem is either polynomial time computable or it's Sharpe hard with nothing in between. Well, Sharpe is the quantitative version of the NB class. It was introduced by Valiant in 1979. Well, by a straightforward adoption of Lander's theorem, we know that there is no dichotomy for the Sharpe class in general. However, for some well-studied counting frameworks such as counting graph homomorphisms and counting CSP, even defined over the general domain, for complexity dichotomy have been established. While for Holland problems, even restricted to the Boolean domain, there are only limited results. Now here, we give the picture as a partial map for the classification program of Holland problems. The starting point is the dichotomy for counting Boolean CSP. So this is the dichotomy for the Boolean version. And this dichotomy has an explicit tractability criteria. And roughly speaking, there are 2 reductions starting from this point. One is to prove dichotomy results by assuming some extra signatures are available. Like for example, like the Holland star problem is a Holland problem where we assume that all unary functions are available. And also, like we may assume some special unary signatures are available. And without assuming any extra signatures, a dichotomy was proved for Holland problems where all signatures are non-negative real valued. And well, we proved a dichotomy for all real valued Holland problems. And before our result, there is a dichotomy for real Holland problems where a signature of orderity is available. And the other direction is to prove dichotomy for some special classes of Holland problem. For example, when all signatures are symmetric. And also there are like for 6-word models and 8-word models. These problems are Holland problems where only a single 4-array signature is available. And so in this talk, we will present a dichotomy for all real-valued Holland problems without making any assumption. And well, as you will see that this result is built on all these previous results, but there are many wholly unexpected obstacles that had never been met in all these previous results. So let's start our journey. Let's first introduce the following classes of tractable signatures. So there are 4 classes. The first one is the set of tensor products of binary or unary signatures. And there are also like signatures called product type or fun type and the local fun type. And this transformable means that they are still trackable after a holographic transformation. We will not go into the details of these signatures, but it's known that the Holland problem specified by a signature set that satisfies this condition, then this problem is trackable even when the signature set is complex valued. Now, in our paper, we prove that the following hardness result. We show that for a set of real valued signatures, if this signature set script f does not satisfy this tractability condition, then the Holland problem is sharply hard. So together we have the dichotomy, but the tractable part is already known, so we only need to prove the hardness part. In order to prove hardness, we need to build polynomial time reductions. A commonly used approach is gadget construction. So given a signature set, we try to build a graph with some diagonal edges such that this gadget can simulate a signature f. If this can be done, then we have reduction from the Holland problem specified by the original signature set f, the script f with this small signature f is just equivalent to the Holland problem specified by this only by this signature set. Well, this reduction is quite trivial. Once this f appears, we just replace this f with this gadget. Well, in this gadget, all vertices are labeled by signatures from this signature set script f. And a simple gadget is merging gadget. So we just connect 2 edges. So technically, we connect them using this binary equality signature. This binary equality signature requires that the assignments of these 2 variables must be equal. So it means that we just merge 2 edges into 1 edge. And a general approach for the dichotomy of Holland problem is by induction. Since we already know that if the signature set contains a signature for orderability, then a dichotomy is already proved. So we only need to consider the case that it consists of signatures of equality. And we suppose that it does not satisfy the tractability condition. Then it's not a set of tensor products of unary and binary signatures. So it must contain a signature that is not in T. Now suppose that the signature small f has RT to n. Now we want to achieve an induction proof by this arity. And the base case is you have a signature of RT4. And this can be done by using dichotomy for eight-verse models and by using dichotomy for weighted orientations. While in this talk, we focus on the inductive step. So for the inductive step, the general strategy is that we start with a signature that is not in T. And we try to use it to realize a signature of lower T that is also not in T. Well, if this can be done, then by a sequence of reductions, we can eventually realize a signature of RT4 that is not in T, then we are done by the base case. This is also a standard approach to prove dichotomy for Holland problems. Since we want to achieve a dichotomy or a complete classification, so we need to classify signatures of arbitrary arities. So we need to use induction to reduce the arity to some finite base cases. And this approach is very successful in previous proofs for Holland problems. And in these proofs, we have unary signatures. So after each inductive step, we can reduce the arity by 1. But here, we can only use merging to realize signatures for low arity. And after each inductive step, we can only reduce the arity by 2. And so we ask the following question. Given a signature of arity n, by merging, can we realize, well, given a signature that is not in T, that is not a tensor product of unary or binary signatures, can we realize a signature that is not a unary or binary signatures after merging? The answer is yes, but only for signatures of arity at least 10. And for signatures of arity 6 or 8, well, there are signatures that are obstacles to our induction proof. Now let's take a look at the first obstacle. Now let's look at this signature, this function of arity 6. This is just well, we can represent its value by this matrix. Well, in this matrix, we use the first 3 variables as the row index and the last 3 variables as the column index. Well, we give the following picture to visualize this matrix. And a block with orange color denotes that there is an entry +1. And a block with blue color denotes is an entry -1. and the other blank blocks are just zeros. So basically, this means that this function on the input 0, 0, 0, or on the all zero input, it gives value 1 plus 1. Now we can check that this signature is irreducible. So it's not a tensor product. So it's not in T. However, by merging, we can show that you can merge any two variables, but you can only get a signature that is in T. So this signature is an obstacle to our induction proof. And in fact, it satisfies the following property that if we can, now so far we can only use the binary equality to do the merging. But from this signature, we can also realize the other we can realize all 4 binary signatures. This includes this binary equality, but it also includes binary disequality and the negative version of the binary equality and the negative version of binary disequality. These signatures are related to Bell states in quantum information theory. And we can show that by merging any two variables of this signature using any Bell binary signature, we can only get a signature that is a tensor product of Bell binary signatures. So this is a serious obstacle to our induction proof. And it takes us lots of time to deal with it. And another obstacle happens when the signature has RTH. This signature is a 0, 1 value function. It has RTH. Still, we give this picture to virtualize this signature. And we use the first 4 variables as a row index and last 4 variables as a column index. And as you can see, this is quite sparse. And if this block has, the origin block means that we have an entry plus 1. And still, this signature is irreducible. And it's not in T, it's not a tensor product of unary or binary signatures. However, by merging, we can only get tensor products of unary or binary signatures. And in fact, it satisfies the following strong property, that by merging any two variables of this signature using any Bell's binary signature, we can only get a tensor product, we can only get a signature, which is the tensor product of this Bell binary signature. So this is the same Bell binary signature that we used for the merging. So after we dealt with all these two obstacles, we can finish the proof and we give an induction proof for the dichotomy of the real Holland problems. The ultimate goal is definitely a dichotomy for complex valued Holland problems. In order to achieve this this dichotomy, we believe that first we need to generalize the dichotomy for real Holland problems with a signature of orderity to the complex valued version. And there are we should also make other steps like for the counting or linear orientation problems. So there's still a long way to go to achieve a dichotomy for complex valued Holland problems. Yeah, thanks. Any questions?
We might have time for one question. We're running a bit behind, but
sorry.
Maybe we have time for one question. If not, we can take questions offline and thank the speaker.
Thank you.
Thank you. So we have one more talk in this session. And Artyom will present a dichotomy for bounded degree graph homomorphism with non-negative weights. So we can begin.
Okay, so can anybody hear me?
Yes.
Okay, so can I actually? Okay, so hi, my name is Artyom Hovarov. And this is a short version of the discussion of the following paper, which is my joint work with Professor Janit Sai. So we're discussing the topic of graph homomorphisms, which has been actively studied for decades. Given to graphs G and H, a map versus of G to vertices of H is called a graph homomorphism if it maps every edge of G to an edge of H. So the modern study of graph homomorphisms goes back to Lova's 1967 paper. We're interested in the problem of counting graph homomorphisms. More generally, we allow the right-hand side graph H to have edge weights. So an edge weighted graph is specified by a symmetric edge weight matrix, Now, for a symmetric matrix A, the following is a definition of the problem eval of A, which counts weighted graph homomorphisms. The left-hand side graph G can have multiple edges, but no loops. This sum of A is called the partition function of graph homomorphisms. Many combinatorial problems can be expressed as graph homomorphisms. These include the vertex cover, the independent set, and the vertex coloring. In all these, the edge weights either 0 or 1. So, for example, the vertex coloring is specified by a matrix that has zeros on the main diagonal and ones everywhere else, forcing any pair of adjacent vertices in the graph G to receive different colors. There are numerous problems coming from statistical physics that are special cases of graph homomorphisms, which includes the Ising model, the hardcore gas model, the Beach model, the Widom-Rawlinson model, and many others, but we will not talk about this. In complexity theory, for exact counting of graph homomorphisms, complexity dichotomies have been shown. That's either the problem sharply hard or computable in polynomial time, that's tractable. The first major result on the complexity of exact counting of graph homomorphisms was obtained by Dyer and Greenfield in 2000. They showed that the problem of counting graph homomorphisms to a 0-1 weighted graph that is simple but possible with loops is either sharply complete or computable in polynomial time. In 2005, Boldov and Groh obtained a dichotomy for non-negative real edge weights. Then in 2010, Goldberg, Groh, Jerem, and Fermi extended it to arbitrary real edge weights. And in 2013, Tsai, Chen, and Liu to arbitrary complex edge weights. So, in fact, Dyer and Greenfield in the same paper also extended the Sharpe completeness to boundary degree graphs. That is, if the tractability conditions are violated, then the eval problem is Sharpe complete, even restricted to boundary degree graphs. This is equivalent to saying that to solve a Sharpe complete problem, for example, the permanent in polynomial time, we need to query the oracle eval of H only on graphs whose degree is bounded by some constant depending on H. This stronger theorem, this stronger version is summarized as the following theorem on the slide. In order to state the next dichotomy by Boldov and Groh, we need the notions of rectangularity and block rank oneness. A rectangular matrix is essentially a block diagonal matrix after row and column permutation, where the blocks have no zeros except maybe a one all-zero block. The matrix on the slide is clearly rectangular and has two non-zero blocks and one zero block. Next, we call a matrix block rank 1 if it's rectangular and every non-zero block is of rank 1. The matrix on the slide is a good example to demonstrate this notion. Here, the first two blocks are each of rank 1 and correspond to non-bipartite connected components, and the last two blocks together correspond to a single bipartite connected component. So, and are each of rank 1 as well. In general, for a symmetric matrix, we can only have non-zero blocks of non-bipartite and bipartite configurations. Now, we can proceed to the dichotomy by Boldov and Groh. It says that for a symmetric non-negative matrix A, the problem eval of A is Sharpe hard unless A is block rank 1, in which case it can be computed in polynomial time. The Sharpe hardness part of the dichotomy by Boldov and Groh to boundary degree graphs was extended by me, Tsai, and Dyer, and here is a formulation of the result. Next, the following is a dichotomy by Tsai, Chen, and Liu for complex edge weights. I'd like to make a few remarks about the paper by Tsai, Chen, and Liu. This is a very long paper, over 100 pages, dedicated to the proof, and the tractability criterion consists of many stages scattered all over the paper and is not trivial to state, so it's not just a variation of block rank oneness as in the dichotomy by Boldov and Groh. So we just say that the problem eval of A is either in polynomial time or Sharpe hard. We also note that the tractability criterion was shown to be decidable in polynomial time. One important thing is that all Sharpe hardness conclusions are obtained by invoking the dichotomy by Boldov and Groh for non-negative edge weights. The proof uses unbounded degree graphs, with the reason being a purification step invoked close to the beginning of the proof. Basically, every non-zero element of a matrix can be represented as a product of a multiplicative combination of a fixed set of generators and some root of unity. Then in every non-zero element, we replace the generators G sub I by the first D primes pi. So element-wise. So now, the paper by Tsai, Chen, and Liu uses various gadget constructions. The following gadget is perhaps the most sophisticated construction used in the proof of the dichotomy. Here, U and V are viewed as distinguished endpoints, and gadgets like this can be used in place of edges of an input graph G. By analyzing its edge weight matrix, the final conditions needed for the tractability are established. Otherwise, the problem is Sharpe hard. As we said, for the dichotomy by Dyer and Greenhill, the Sharpe hardness part was additionally extended to boundary degree graphs by the authors in the same paper. And for the dichotomy by Boldov and Groh, the same was done by me, Tsai, and Dyer. It remained an open question whether the same can be said about the dichotomy by Goldberg, Roger, and Thurley for real edge weights, and the more general one by Tsai, Chen, and Liu for complex edge weights. We also remarked the complexity of counting graph homomorphisms for boundary degree graphs is particularly interesting because most partition functions from statistical physics are considered in boundary degree graphs. Also, much work has been done on the approximate complexity of graph homomorphisms focused on boundary degree graphs. In many cases, approximate algorithms have been achieved. Now, a main result of the presented paper is that we have extended the Sharpe hardness part of the dichotomy by Tsai and Liu for complex edge weights to boundary degree graphs. So, in terms of the main proof structure, our paper is comparable to that by Tsai and Liu. We first have a long setup for the main proof, which includes two new notions: multiplicative block rank 1 and a related notion, modular block rank 1, both generalizing block rank 1. Then we have two crucial ingredients. After that, we proceed to the main proof using the so-called meta-arguments to utilize the proofs from the paper by Tsai and Liu. These meta-arguments are based on some fundamental observations about the proof patterns from the paper by Tsai and Liu. We will also need the notions of thickenings and stretchings. A P thickening is just replacing an edge by P parallel edges, while an R stretching by paths of length R. Here is what a thickening and a stretching of an edge look like. As we said before, the proof by Tsai and Liu made use of various gadget constructions in place of edges of an input graph G. We call them edge gadgets. So an edge gadget is simply a graph with two distinguished endpoints. Our proof revolves around edge gadgets, and they are the central object in it. Previously, we mentioned edge weight matrices of edge gadgets. For the current problem, ELFA, it's useful to have the following notation for them. So next, we introduce two crucial notions: multiplicative block rank 1 and modular block rank 1. In essence, we call a matrix multiplicatively block rank 1 if for some positive integer k, its kth Adamar power, its block rank 1. The symmetric matrix on the slide is clearly multiplicatively block rank 1, and we can take k to be 7. So when we power it to 7, we get two rank 1 blocks. Moving on, we call a matrix A modular block rank 1 if the matrix comprised of the absolute values of the entries of A is block rank 1. We have the following trivial implications. More importantly, we will need the contrapositive of the second one. That is, every non-modular block rank 1 matrix is automatically non-multiplicative block rank 1. With that said, we can proceed to a first crucial ingredient. We prove that non-multiplicative block rank 1 of a symmetric matrix A implies Sharpe hardness of the problem L of A on boundary degree graphs. The proof is modeled after the one for the non-negative case by me, Tsai, and Dyer. However, there are some substantial differences. In particular, we come up with a more appropriate gadget design and make use of the so-called Vandermonde argument. So, for example, gadgets like the following pentagonal gadget are used to replace every vertex of degree 5 in the graph G. So the bundles of thickened edges are for the purpose of applying the Vandermonde argument. We also have the following corner case gadgets corresponding to d equals 1 and 2. Namely, the case d equals 1 corresponds to loops and d equals 2 to two parallel edges. The following is a simple argument that we call the Vandermonde argument. So, for example, working over the complex numbers and assuming the displayed equation holds, we can conclude that the following linear combination of conjugates is 0. We'll actually need the contrapositive. That is, if a combination of conjugates is non-zero, then a combination of some fixed Adamar powers is also non-zero. Next, we state the following transfer procedure, which is our second crucial ingredient. Basically, it says that if we have an edge gadget whose edge weight matrix in the purified world is non-multiplicative block rank 1, which is true if it's not modular block rank 1, then there exists a thickening of this gadget whose edge weight matrix in the non-purified world is also not multiplicatively block rank 1. The key idea here is to use the fact that every finitely generated field contains only finitely many roots of unity, so they form a cyclic group. So, having completed the preparatory steps, we can now outline the main proof. We follow a similar structure to the paper by Tsai and Liu. The difference is that the purification step is not available. So instead, we keep the matrix A in its purification _ A and pass them to the next stages instead of just only A. By using what we termed as meta-arguments, we can actually invoke the corresponding proofs from the paper by Tsai and Liu. And here we make a crucial observation about those proofs. In case of Sharpe hardness, an edge gadget with a non-modular block rank 1 edge weight matrix is constructed every time, and therefore in the non-purified world, this reflects back to a non-multiplicative edge weight matrix by the previous transfer procedure. This way, our first crucial ingredient, we conclude the Sharpe hardness of the problem L of A on boundary degree graphs every time unless A satisfies additional constraints. If A satisfies all import constraints, then we show that the problem L of A is Sharpe. So, having finished the proof for boundary degree graphs, we then extend the Sharpe hardness part further to boundary degree simple graphs. We prove the following lemma, which allows us to replace every edge gadget by a simple edge gadget, and with no edge between the endpoints. The proof actually is crucially reliant on the following isomorphism result by me and due to me and psi. So and thus Sharpe hardness for eval of A on 1 degree simple graphs follows. So now we can proceed to the decidability and constructivity parts. So the tractability criteria in the paper by Tsai and Liu in our proof both result in the same tractability conditions on the matrix A, and so the polynomial time decidability applies to our dichotomy as well. Next, we show that our dichotomy is fully constructive in the sense of the theorem on the slide. The original proof from the paper by Tsai and Liu is not constructive in this sense, and many steps are highly non-trivial, such as the so-called pinning lengths. However, in our proof, we carefully avoid or fix each non-constructive step, and so the overall constructivity follows. And so this completes my talk. Thank you.
We have a few minutes for questions.
Okay. I forgot to show my face. Okay. So. Questions?
Yes.
Can you hear me?
Thomas, we can't hear you very well. Could you increase the volume?
Yeah, I mean, I was not able to access Slack. Maybe you can ask them, real time, or just yeah, I can answer them offline. So
I think Thomas has a question, but we cannot hear you very well.
Can you hear me now?
You can join.
Very faintly, but yes, if you can speak very close to the speaker, that'd be better.
Okay.
To the mic, I guess.
Well, I'm generally wondering if I compare
Can't
this
hear.
dichotomy theorem with the original one that was proven 2015 at FOCS, the between NP complete and P. I'm wondering why. What are the difficulties?
Can you speak louder?
Can you hear me?
Can you speak a bit louder?
Yeah. Can you? I'm wondering. Is it better now?
Way better.
Okay. I'm very loud now here. If I compare this dichotomy theorems with the original one between NP completeness and P that was proven 2015 by Butalov and so on, and if I compare this, what are the difficulties? I'm wondering what are the difficulties for establishing a dichotomy between sharp P completeness and P. What are the difficulties for completeness? Maybe is it because
the ones by Bulatov, about the NP completeness, they are decision versions, right? So yeah. We're doing counting, these are counting versions.
And Suk did another one the uniform, the other the non-uniform case.
Ah, okay. Can you?
There were two, yeah. And so just an idea. Maybe it is possible, or also a question, to extend that to P space completeness. Another. Just to leave it open.
I'm sure that no. Wait. I'm not sure it's a P space completeness.
The future dichotomy between P space completeness and P, with a different approach, maybe.
Maybe, yes. Because I'm not sure that there are. If it's Sharpe hard, that is, for example, you want it to be like if it's Sharpe hard, then it's P space complete, something like this.
No. Why is it not Sharpe complete? So maybe there's some room for extension.
Complete because you're taking Sharpe hard because the answers are not non-negative integer numbers. Because if you take complex numbers, complex edge weight matrix as an input, right? The answer is a complex number. Complex algebraic number basically. And so when we talk about Sharpe completeness, the answer must be a non-negative integer. So if it's for example, the dichotomy by Dyer-Ingram, I said it's Sharpe complete because the answer is a non-negative integer number. But starting with the dichotomy by Bulatov and Groh, the answer is a non-negative real number, for example. So
I see.
You cannot even talk about Sharpe completeness. It doesn't make sense.
Yeah.
So in a way, it's kind of sharply complete because you can always compute. The answer to a problem is always a complex algebraic number. But you can compute the constituent parts. The integer numbers. So basically, this number is comprised of many parts. Yes, and each can be computed. So in a way, it's almost like sharply complete.
I see.
It's like it's going to be like, yeah.
Okay, thank you.
So we're technically out of time for this session. Let's thank the speaker and take the rest of the questions on Slack.